So in this talk, I would like to share my thoughts about security research in the industrial lab. So let me first talk a little bit about myself. I graduated right here in 2005 with a PhD degree. And then I joined Microsoft Research for 12 years, and currently I'm a senior researcher there. I have been working on various security topics, but mainly on security about browser, HTTPS, web protocol, and mobile apps. And in the past few years, I have been really focused on program verification for security. For security problems. And during these years, I have initiated a number of cross-company efforts to address browser HTTPS issues and web protocol problems and the information feed problems. And I also gave talks inside and outside of Microsoft to increase developers' awareness of this kind of security problems. I'm also involved in the academic community. I serve on the program committees of leading security conferences and the thesis committees of students in several universities. Now, as I said, the goal is to share some of my thoughts about security research. I will start with three questions. First, why is security research needed in the industrial, in a company? And what are the differences between an engineer role and a research role? Then what are the strengths and the weaknesses of a researcher? Then based on that, the main body of my talk will be I will suggest three types of research opportunities in actual engineering environment. And in the end, I will briefly talk about the transition from a PhD student to a researcher. So first, I like to set the context of the talk. So these are just my personal opinions. I think whatever I say, I hope they will be valuable to you, but they may not fit. They may not suitable in all your cases. And the second thing is, these are things coming from my positive experiences as well as my lessons learned. So these are things that I believe that they are good things, but not necessarily something that I have achieved. I also like to clarify what I mean by security researcher in this talk. A security researcher typically receive a PhD degree and work in a research lab, and to some extent is involved in the academic community. And in particular, I'm not talking about black hat researchers, who are also known as sometimes known as security hackers or security researchers. So the reason is I'm not familiar with black hat kind of career. So this is perhaps I should say industrial researcher working on security problems. Now, first question is, why is security research needed in a big company? I think the first reason is big companies' business is really based on trust. And this is especially true when we talk about the cloud computing. For example, Microsoft, a lot of business is based on the cloud platform, the Azure platform. So the thing is that oftentimes customers want to onboard onto the cloud platform, like put data or services onto the Azure platform, but they care about trust. So you have to give customers a kind of confidence. And the second reason is security is constantly evolving because of changes in software architecture, trust relation, hardware assumption, and regulation, compliance, these kind of things. And a company needs people to work beyond product cycles in order to look into the future. And the third reason is about the knowledge pool and the data pool. Security is not something that you can see or touch. Not like some multimedia or virtual reality, you can really sense that. But exactly because of that reason, I think the in-depth research is very important. Otherwise, the company will not know what it doesn't know. It's very important to have somebody to look into this kind of deep problems. And research activities can keep a deep intellectual connection with the broader community, the academic community. That's how a company can build the knowledge and the data. Now the second question is, what are the differences between an engineer role and a research role? So I would like to say that both are about engineering. What I mean by that is engineers are doing productization, so their work items are tightly integrated into product schedules. However, I will argue that researchers are also doing engineering, except that it is more like a prototyping style engineering, which follows the self-driven multi-year agenda with engineering goals that can be articulated and prototypes that can be demonstrated. So still, it is engineering. So what I meant by that is we shouldn't think about research and engineering in contrast. So the research is a component in the longer term engineering. So later I will say that understanding the actual engineering constraints is a big research contribution. It's very useful. And the third question is what are the strengths and weaknesses of researchers? I think typically as researchers, we have the ability and the luxury of time to explore problems by ourselves. And we also get more opportunities to get exposed to new ideas in the broader community. And also the PhD style of thinking can bring a novel perspective into the real-world problem. However, researchers are usually weaker in general engineering skills, and we tend to have some indirect views about the real. So that's why I think a way for a researcher to really contribute is to find opportunities to complement the work that engineering teams are doing. So that means researchers shouldn't simply help engineers do things that they are already doing, because we were not do the work better because our general engineering skills is not as good as full-time engineers. On the other hand, we shouldn't just advise or consult. Those things are not very concrete. So instead, we should build our prototypes to demonstrate new things. So then these lead to the main body of this talk. I would like to suggest 3 types of research opportunities in an actual engineering environment. So the first opportunity is a researcher should take a holistic view on security engineering, on the real system, the real world system. And the second opportunity is to understand engineering challenges for a technology that academics may feel overly optimistic about, and then develop a new technology that is really feasible in the environment. And the third one is it's almost the flip side of the second one, which is we should understand engineering context and turn a pessimistic theoretical result into a useful technology. So, okay, so the first opportunity about the holistic view on security, we all know that computer systems are very complex. So they are usually they are always built through collaborations of different teams, and they are increasingly interconnected, even across multiple companies. And engineering teams are naturally staffed by components and features, but when we think about security, it's really a global property. And that's why a researcher's holistic view about security can provide a complementary value to the engineering team. So let me use my own research as an example. So I think that most of you know that HTTPS promises to provide end-to-end security, which means if you have a browser, if you have a HTTPS server, then no network node, intermediate node, can see or tamper with the information. That's the whole purpose of HTTPS. So if you use a proxy, the only thing the proxy can do is to establish an SSL tunnel, which just forward the encrypted data back and forth. So the proxy shouldn't see anything meaningful in the communication. However, we found that in 2009, we found that all browsers at that time had a class of problems which completely defeat the purpose of HTTPS. And these problems are due to cross-chain issues. So let me explain to you the architecture of a browser. So at the bottom, of course, we have the network layer, and then we have this either HTTP or HTTPS layer. And on top of that is something called the rendering engine, which renders HTML page and renders JavaScript, runs JavaScript. So in fact, people who build the communication layer are very different from people who build the rendering engine layer, because for the communication layer, these are the people who usually build something like SSH or Telnet. They deal with network packet, not network packet, but some network data. And on the top level, these are the people who usually build Microsoft Office, Word, PowerPoint, this kind of things. So they deal with documents. So the interesting thing is that at the rendering engine level, everything is a plain text document. There is no encrypted document. So the encryption ends here by HTTPS. So that means usually a lot of details at the HTTP level is completely transparent to the rendering engine level. So that means the rendering engine level doesn't always know whether a document comes from an unencrypted channel or an encrypted channel. And that is a very important area, a cross-team area that has been overlooked. So for example, one of the problems that we found in all these browsers was the handling of 502 error page. So what happened here is that suppose the browser tries to access https bank.com, then in this case, the browser and the web server are benign, but the proxy is malicious. The proxy tries to steal information from the communication. So in this case, this malicious proxy can just send a 502 response, which is essentially server not found. Okay. So the interesting thing is that obviously at this point there is no SSL handshake, so there is no encrypted tunnel yet. So what happened is that this proxy page, 502 page, is actually delivered to the rendering engine level. So it is rendered in the browser, which is very, very interesting. And it is rendered in the context of HTTPS bank account. All the browser's behaviors is like this. So of course, then the proxy, inside this proxy page, it may contain something like a frame. A frame is essentially a container for a page. So this frame, once again, makes another request to HTTPS bank account. But this second time, the proxy established the SSL tunnel so that the request can go all the way to the real server, and then user sensitive data flows back into the browser, encrypted. So of course, at this point, the proxy cannot see the data because it is inside the tunnel. However, now you can see that both the green page and the red page are considered by the rendering engine as if they come from the same domain. So if you know about browser security, the security policy is that documents in the same domain is able to access each other. So if you run the script in the green page, the page is able to read the data from the red page. So essentially, if you put this whole scenario end to end, essentially that means the proxy is able to read the sensitive data or even write into this one. So you can see that essentially this HTTPS end-to-end security is broken, although the proxy doesn't break any good part of it. It's all about the interaction between different components. Right? So I think that the interesting thing is if you think about the problem, who should we blame? We can blame the communication layer because the 502 page shouldn't be delivered if the SSL handshake is not successful. Or we can blame the rendering engine because the rendering engine shouldn't render the page in the same context as a successful HTTPS page. Right? You can, but who to blame is not an important thing. But the reality is that product teams are usually staffed according to components, but security is a global thing. We have to examine security. We have to examine how different teams interact with each other. So that, I think, is a good complementary value we can provide. Now, here is another example which shows that security problems can even exist across different companies. So in 2011, we did a study about online payment protocols and e-commerce, and we found that there are many issues in the integration logic, which allowed us to essentially do free shopping, so we can buy things without making payment. So all these things are because of some kind of logic gap between different browsers, different websites. So for example, let me explain one of the issues. So in this scenario, we have two servers. One is Amazon, which this is actually Amazon payment service. Amazon payment service, which we call the cashier. You can think of this like PayPal. And then there is a merchant website which we call Jeff. Now this, suppose we have an honest shopper, Chuck. And Chuck can say that I want to buy a DVD from the website. Then the protocol is the following. Then Jeff says, hey, please bring this letter to the cashier. Now this letter says, this order 123 is $10. When it's paid, please call this please call this callback URL. So there is a field called callback URL in the code. Now this shopper simply forward this letter to the cashier. Then the cashier, of course, will transfer $10 from the shopper's account to Jeff's account because he sees that Jeff is the seller. But after that, Amazon will call the callback URL, and then Jeff gets notified. And Jeff's logic is that Jeff will check the signature to make sure that this message is indeed from Amazon. And it checked it is $10, that's good, and the order ID is 123, and order 123 is indeed in the pending state, so everything looks good. However, this protocol can have a very serious problem because you know that everybody can register for an Amazon seller account. So now consider a malicious shopper. This malicious shopper truck can also register for a seller account called Mark. It's just some account called Mark. Now he can play the same protocol, first two steps. Now, instead of forwarding the original letter to the cashier, he can just copy the letter but put Mark's signature. Essentially, because he has Mark's signing capability, so we can sign the letter as Mark. Now, in this scenario, what the cashier sees is the truck is buying from Mark at this stage. So that's why the $10 is transferred from Chuck's account to Mark's account. But after that, Amazon will call the callback URL, and Jeff gets notified. But in this case, you can see that Jeff still check this is Amazon signature, the order ID is correct, and the amount is correct. So Jeff is happy. So this transaction is completed. Although what happened is that this guy just transferred money from one account to another account. Please.
So Amazon have two callbacks or just one?
Just one.
Why only one? If both of them reach to Amazon, why only one? If both of them reach to Amazon, Mark and Jeff Merchant. How was the callback chosen?
Oh, the callback. The callback is Jeff generated this callback. Jeff indicated this callback in the first response. But what the shopper does is simply copy the entire letter containing the callback, the exact Jeff's callback, but signed with Mark's signature. Right? So yeah.
Why aren't those callbacks tied to the signature itself?
Sorry.
Why not tie the callbacks to the signature itself? Why not just like have Amazon have a database of the signature as this callback instead of trusting that the shopper is going to send you the callback correctly?
Yeah. That I think that is related to perhaps the flexibility you want to provide to websites. So if you think about these are really two identities. The callback URL is the identity of the website, and the signature is more about the identity of the seller, right? So, for example, this seller can be company food, but the domain name can be perhaps buy.com. So this kind of association it's not that obvious. Right? So that, but anyway, this was how they designed the protocol. Here is another example, which is about single sign-on authentication. I think perhaps most of you have used the single sign-on, like a Facebook login and Google login, and we studied this kind of problem and we found similar problems in the integration logic. So before 2012, Google ID was based on a standard protocol called OpenID 2.0. The protocol itself is very, very complex, but this is perhaps the simplest explanation I can come up with. It has only 2 browser redirections. So a browser redirection is just a message generated by a website and passed to the browser. If the browser is honest, the browser should pass this exact message to the destination server. Okay, this is called a browser redirection. So in this protocol, the first redirection indicates the relying party's identity and also required equals email first name and last name. So what this means is the relying party pass this to the Alice, and Alice pass this to Google ID. This means I want Google to return another redirection which contains this person's email first name and last name, and also there is a field indicate which fields are included in this message. Then we put a signature. You can think of this as a signed envelope containing 3 pieces, a number of fields inside of it. Signed envelope. Okay, and it looks really straightforward. When the relying party receives this redirection tool, it can authenticate. It can log this person in as Alice.com. However, this can also be a problem in reality. For example, suppose now we are talking about a malicious user Bob. Now what Bob can do is simply remove email from the request, so that now from Google's perspective, you are only asking for first name and last name. Now, of course, Google will return a signed envelope and containing only first name and last name with a signature, but Bob can attach another field, which is email equals alice@me.com. Now you can think of this scenario as there is a signed envelope, a very good signature, but there is a yellow sticker outside of the envelope. Right? This kind of response. Now it's now getting a little bit tricky because the relying party website, a lot of them are using a library, a Google ID library, and that library has a method called the name is called a validate message. So relying party code just called the validate message, which simply check the validity of the signature and return true, because because in this case, indeed, the signature is fine. But after validate message returns true, then the relying party just take the email field and sign the user in as an email call. So again, when you piece together all these things, you will realize that there will be some kind of logic gap when you consider different developers jointly put together the system. Yes.
So here, did the lapse in security come from, not from a problem with the protocol, not from the Google Libraries implementation, but the guidance that was provided, or the standard way that clients use the library?
I think this is a very, very, very good question. I think if we only saw this kind of one or two this kind of problems, I would tend to see this as individual developers' fault. But the thing is, we have been looking into this space for a long time, and I think right now my view is that there is a class of integration problems which you cannot just blame the developer, because in this case, in fact, in this particular case, I believe the solution was eventually Google decided that they fixed the problem. They retired the library because this library itself is already very, very confusing.
So this is an example of man-in-the-middle attack. Aren't there protocols like TLS or RSA encryption just to prevent that with your standards now?
Okay. Actually, this is not a man-in-the-middle attack. So the example that I gave about HTTPS, that is to attack the end-to-end communication, man-in-the-middle of the communication. So in the shopping example and the single sign-on example, there is no network man-in-the-middle. So I think what you meant by man-in-the-middle, you seem to consider the browser as a man-in-the-middle. Is that?
Yeah.
Yeah. The browser is never considered as man-in-the-middle because browser is really an endpoint of communication. Right? So if we are talking about TLS, HTTPS, then the attacker should be somebody sitting on the network between the endpoint.
I have two questions. The first one is, why just get the Bob router out of the communication? Because it seems to me that there's no point for putting Bob here.
Yeah. So that there is a very important thing I didn't talk about, which is why Google knows this browser represents Alice. It is because there is this browser has signed into Google as Alice. So you have to, if this guy, if the relying party directly make a call to Google ID without going through the browser, then it's basically asking who this person is without asking this person to forward. Right? There is no notion of this person.
Sure, but why don't Google just directly return the credential to the relying party website? Why does that have to go through the browser? The return message.
Okay, so what you are saying is redirection 1 still goes through the browser, but this directly respond to the, then again, it's almost the same situation where you don't know. Now, you only know that at this point, Alice is signed in, but from which browser? Right? You want to tie the browser into this communication.
Apart from that, is there no checksum done in between? Like the whole protocol just let whatever the user to mess up with the data, and there's no checksum preventing that.
So in this protocol, the first redirection doesn't have any signature, and the second one has a signature, but this signature only covers certain fields, not the entire message. This is how they designed this open ID protocol. So, okay. So I think I explained what I meant by take a holistic view of security, and I think the second opportunity I want to stress is to understand engineering challenges for a technology that academics feel optimistic, but we need to develop a new technology that is feasible. So many years ago, I had a conversation with a very senior person, and he asked, why are these logic bugs still research problem? Because formal methods and program analysis tools are exactly designed to deal with, to prevent this kind of logic bugs. And I said, but companies are not using this technology as a whole. When you write code, you just write code. You prove it, use any tool to prove it. And he was saying, that's unfortunate, they should use. And his point is that the research is done, so the rest is just engineering. I think this represents a very typical view about research and engineering, which I don't quite agree. But let me use an analogy to make my point. You can say that, you can ask why obesity is still a research problem, because people show that if you spend 40 minutes per day on the treadmill, then the problem is solved. But then most people do not spend 40 minutes a day on the treadmill. Then you can say, this is unfortunate, they should do that, but research is done. You shouldn't do more research. There's no valuable research. This is my view is that unlike theoreticians, we shouldn't think the research is done when the real world problem is, and it is valuable research to understand the real life constraint. For example, in the treadmill, perhaps the lower class can afford the treadmill. Is there a research to lower the price of treadmill, or the middle class cannot afford the 40 minutes, so maybe 40 minutes is too much. Maybe 10 minutes will make a difference. So these are the things we can think about, and that lead to my current research effort, which is called self-verifying execution. It is a novel way to utilize program verification technology to prevent logic bugs. So the goal is to make verification technology more usable for real developers. And not surprisingly, our current focus domain is protocol implementation. I explained before. So I don't know how many of you have experience about program verification. So I think if you don't have first-hand experience, perhaps you think about this program verification as a black box. So you can just feed the source code of a program and a property that you want to ensure into a black box, then somehow the bugs will be discovered automatically. But in reality, program verification is very challenging. That's why it is not widely used. So, for example, of course, you have the code, you have the property, but very importantly, in order to prove your property, you need to model the underlying system, which is very difficult to be precise. Then you also need to model the hypothetical attacker. This attacker, this is very difficult to be exhaustive because usually you don't know what the attacker can do. And then after that, the theorem you want to prove is no matter how the attacker interacts with the system, this even for an infinite number of times, then this safety property is always true. So this will get you into a situation where you need to do inductive reasoning, which is perhaps the most difficult part about formal verification, because you need to come up with something called a loop invariance and some good lemmas, then the proof to make the proof go through. So that is very, very difficult. So the idea of self-verifying execution is that every actual execution is responsible for collecting its own executed code and then proving the property in the end of every execution. And let me give you a simple example. So consider a system with 3 websites: alice.com, bob.com, and charlie.com. And each of them has a constant, integer constant, 40, 10, 40, and 5. And then they also have public methods like grab, compare, and finish. Now, these 3 websites are collaborative. They want to run the protocol to decide which they want Charlie to decide which website has the largest integer of the 3. So, and of course, the execution is driven by the client. This client is completely untrustworthy. The behavior is arbitrary. Now here again, the safety property we want to prove is that whenever conclude M2 is reached, M2 must represent the largest, the website holding the largest integer. This is what we do. So you can, I think many of you may think about this expected protocol flow, which is the client calls, sorry, so I didn't explain that these 3 methods. The first method, grab, is to return Alice value. Then compare is to compare Bob's value with the value in the incoming message. And finish is to compare Charlie's value with the value in the incoming message and make a conclusion there. So that's the public methods. So you can expect this kind of execution. In the beginning, you call grab on Alice, then compare on Bob, then finish on Charlie. And in this case, indeed, you get the result 40 Bob, which is correct. However, it doesn't mean that the system is secure, because another client may just call grab and then use the result to call finish directly. In this case, you end up having 10 Alice, which is incorrect. So typically, in the traditional verification approach, you need to build the runtime platform, and then you need to build a model for this hypothetical attacker, which hopefully can exhaustively exercise all your execution paths. So after that, you try to do an inductive proof, and you should stuck somewhere, and then you realize there is an attack. It's a very demanding task to prove or disprove this kind of thing. But But the self-verifying execution is much simpler. All we need to do is, in the protocol, we add another field called a symbolic transaction. And the first message in the first call, grab, then the grab will return the value as well as this representation, which is alice.com hash grab. And hash grab is a hash value that we compute over the executed code of the grab. So this represents the code. And this protocol can run as we saw before, but in the end, we get 40 bob and this long SIMT, symbolic transaction. Now, whether this result is correct, we can use a program verifier to prove that whether this final SIMT is sufficient to imply the safety problem we want to ensure. So this, for example, if our execution indeed goes through grab, compare, and finish, then the program verifier is able to prove that this sequence of logic, this sequence of code, can already logically imply the safety problem. However, in the attack situation, if the code only goes through grab and directly finish, then the program verifier will not be able to prove this property. So the execution is rejected at runtime. So you can think of this self-verifying execution as so the verification here is still symbolic, meaning that it only considers the code, but not the there's no concrete data involved in the verification. So you can think of this as a middle ground between traditional offline symbolic verification and runtime concrete checking, because we are doing symbolic verification at runtime on a per execution basis. This is, I think, it's pretty interesting thing. And also another advantage of the approach is that all the theorems can be effectively cached because they are all about code, no concrete data. That means at runtime there is almost no overhead if you are executing a normal code path. Only if an attacker tries to somehow execute a different path, then that will trigger another theorem. Alright, so I guess I need to skip a few slides. So the third opportunity that I see is that researchers should try to understand engineering context and turn a pessimistic theoretical result into a useful technology in the end. So usually we often have some pessimistic theoretical result if we don't consider the specific engineering context. For example, we know that the halting problem is unexcitable. However, researchers in MSR Cambridge have developed very powerful analyzers to detect infinite loops and deadlocks, essentially to determine whether programs terminate. So that is because oftentimes the real problem people care about is whether certain real-world programs terminate, rather than coming up with some super algorithm to decide whether every possible program terminates. That is more on the theoretical side. And then similarly, the set problem can be complete, but if you consider today's set solver, they are able to just solve very, very complex problems. and there are some very important algorithms like stochastic gradient descent, which is heavily used in AI deep neural net training. And the algorithm is inherently sequential. That seems to suggest that there is no way to use GPU to speed up because it is sequential. But recently, researchers in Microsoft Redmond have found a way to make it parallel by with some negligible accuracy loss. But it turned out that this is perfectly okay when you consider machine learning, because machine learning can tolerate this amount of error. So, okay, so I'd like to talk a little bit about the transition from a PhD student to a researcher. I think there are a number of changes to expect. The first one is, as a PhD student, usually a PhD student plans research according to some application goal. So that tends to be a shorter term. And for researchers, it is good to plan a project as a multi-year agenda. And the second thing is, no advisor, but there are many colleagues who can inspire you. So that is something we need to take advantage of. And also, it's good to read the papers, but it's perhaps more important to spend significant time studying real-world systems to make it, to do research. And, so I think that I'm almost out of time. So as a summary, I think that I want to share with you 3 opportunities for researchers in the industrial lab to make a contribution. So the first one is to take a holistic view about a multi-team, multi-company system. The second is to understand engineering challenges of a technology and try to develop a technology that is feasible in reality. And the third one is to put a theoretically hard general problem in an actual engineering context to identify the specific problem with solution. And I think it's good to think about research as a component in engineering. That means, as a researcher, we should motivate our research by engineering problems and also validate our research result in the engineering environment. Okay. So finally, I would like to say that collaborations between universities and industrial labs are always beneficial to everybody. So they happen all the time in MSR, and usually the internship is a nice way to start a concrete collaboration. So, and as a student, I did several internships. Now I'm a researcher. I have met quite a number of PhD students, and they often came out with fantastic ideas. So I really encourage students to do internship in industrial labs. So that's it. Thank you very much.